Hi, my name is Jason, and I'm a third-year undergraduate at MIT studying mechanical engineering. Our team is excited to present an advanced thermal storage geothermal district heating and cooling system to decarbonize the built environment, starting with all colleges and universities. Buildings contribute a disproportionate amount to greenhouse gas emissions. Clusters of buildings, like colleges and universities, often contribute more carbon emissions than average commercial or residential buildings. For example, research universities like Harvard and MIT contribute a whopping 63% of all Cambridge city-wide large building emissions. Most of these campus emissions come from building heating and cooling. However, despite the urgency and need for leadership, universities are uncertain of how to achieve even 2050 decarbonization goals. The main barriers that solutions need to overcome are affordability of the technology and the need to minimize disruption to campus activities. In order to address these issues, our team has identified an advanced thermal storage HVAC system design combining geothermal heat pumps with thermal energy storage to offer an optimal approach to building heating and cooling, while still being cost-effective and low risk. Existing systems used at universities like fossil fuel burners and boilers will never be able to reach carbon emission goals. However, alternatives on the market are either too expensive or don't have the climate impact needed. Our approach utilizes a distributed network of water source heat pumps that are installed at each building rather than a central location, which allows them to be custom fit to the endpoint of use and minimizes distribution losses. The heat pumps are all connected by a shared water loop that transforms these clusters of buildings into a shared energy network. Also connected to this loop are underground thermal batteries, the newest of which are coming from DOE's Oak Ridge National Lab, utilizing crystal formation. During off-peak hours, where electricity demand is lower and cheaper, extra energy is stored in the underground thermal batteries. During peak hours, when electricity demand is high and more expensive, the thermal batteries release energy to the heat pumps to meet the building loads and save costs on paying for more expensive electricity due to the grid variability. This system allows heat to be continually recycled and reused for maximum efficiency and significantly lowers the cost of heating and cooling. We are targeting a huge market with 3,777 US colleges that could be impacted in the total addressable market. Our focus currently is to implement and commercialize the technology for the 377 colleges in our obtainable market, which have 337 colleges who have committed to net zero by 2050. To reduce upfront capital expenses, we retrofit existing infrastructure like the existing piping network connected to buildings at colleges, which can eliminate many of these costs. We're developing financing plans through partnerships with banks to lease equipment to address capital expense challenges for universities that have smaller endowments or funding. Lastly, we aim to take advantage of governmental tax credits and available federal funding from the Inflation Reduction Act to cover most, if not all, costs. For MIT, these funds could be as much as $75 million. These strategies will help reduce the initial cost barrier but may prevent colleges from decarbonizing. Implementing our system design also has significant operating expense savings. Water source heat pumps are currently the most efficient heat pump available on the market, with efficiencies 4 to 6 times greater than electric boilers. Heat pumps are also reliable, with a life cycle of 25 years. Since the system is decentralized, repairs can happen quickly on site and won't disrupt campus at large. Additionally, an estimated 25% of HVAC needs will be free under this system because of the ability to share energy in the building district. If one building is cooling and rejects heat, another building that may be heating can recycle the waste heat for free. With these operating expense savings, universities will save 20% annually on electricity, resulting in a payback period of around 5 to 10 years, depending on the exact size and implementation of the system. They will at least break even with the upfront cost they pay for the project. Our implementation strategy for the system design is made of 3 phases. In the first phase, we approach universities with plans and acquire them as partners by explaining the benefits of implementing the system on their campuses. Simulation and modeling tools we're building will help expedite this process and illustrate the possible energy savings and emission reductions through an assessment of the campus site. Additionally, a demonstration pilot project on a small clusters of building can be done. Our team has recently received approval for a pilot project like this on the MIT campus. In the second phase, we aim to address any concerns about the project, including developing financing plans to address cost barriers. After receiving approval, we'll move on to the third phase where we connect the college with the relevant design and construction firms who will manage the installation on campus. At each step of the process, we've identified key resources and entities needed to be successful. In the initial phase, student advocacy will play an important role in pressuring universities to critically consider adoption of geothermal as a way to decarbonize. As the project develops, design firms, manufacturers, and banks become involved in implementation. To address the concerns of campus disruption during installation, our implementation is based on building clusters. This is a map of MIT's campus divided into separate clusters of buildings. The system can be solved at one cluster at a time because it's decentralized, and thus a phased approach to implementation can be taken so that campus operations aren't adversely affected. The cluster of buildings shown here is where the pilot at MIT will first occur. Our financial model is to generate revenue based on commissions from successful completion of projects. To help jumpstart our operations, we've received funding interest from investment firms looking to enter the clean energy space. With this model, we believe that positive cash flow can happen within 3 years through a successful acquisition and pilot of 2 colleges. To scale up to multiple colleges, our plan to commercialize beyond just our work at MIT includes 3 major activities. We're developing educational programs and training modules to do outreach at more universities. This is currently happening at Wellesley and Harvard as we look to expand our work in the Boston-Cambridge area. Modeling tools are also currently under development, which will allow us to expedite the process of site assessment at universities by showing them a digital twin simulation of their campus. Lastly, we will continue our ongoing efforts with acquiring partner colleges, targeting universities with the highest emission contributions. Historically, Black and minority colleges and surrounding communities disproportionately burdened by the high cost of HVAC upgrades are often left out of the energy transition. Energy justice requires equitable access to comfortable and affordable living environments. By taking advantage of tax credits and federal funding, together with our advanced approach to cost-effective HVAC, these colleges can readily overcome the initial cost barrier of installation for their communities. This initiative also empowers students to take leadership roles and advocate for the future in the energy transition. We are at a crucial crossroads in the climate crisis, and we must decarbonize now. Our hope is that our work will inspire other students to join the cause in rapid decarbonization at their campuses.